Now let's look at the tank simulation I created for Todd. We are using PID controllers in this simulation, and PID is an acronym derived from the terms proportional, integral, and derivative. Proportional represents gain, integral represents time, derivative represents lag time. A PID controller, when placed in automatic mode, continuously calculates the error between a desired set point and a measured process variable and applies a corrective action to the output using proportional, integral, and derivative constants. Derivative is not always required, and if not used, the controller is referenced as a PI controller capable of derivative. For this video, we will only use proportional and integral. Proportional, or gain, is relatively easy to understand. When a set point is entered into the controller through a graphical faceplate, much like a home's thermostat, an error is instantly produced between the process variable and the new set point. The error was multiplied by a scale factor, the proportional gain, and immediately applied to the output. The process variable will move in the appropriate direction to begin correcting the error. Let's examine the model and determine what factors might influence the level in the tank. We have determined that the set point will be 50%. If the actual fluid level is at 55%, what would the control output be if the gain is set to 3? We have determined if I make a new set point adjustment, lowering the level from 55% down to 50%, at the moment I enter the set point at 50%, with a proportional band gain of 3, the output will drive down to 35%. Without the time-based corrective factor that integral provides, a PID controller in only proportional band mode will control at an offset, never achieving set point. Once the set point is entered and the gain is applied to the error, the proportional gain's job is done, unless integral initiates an evaluation of the error. Integral, when correctly calculated, initiates a review of the now smaller error based on the calculated time constant. The error over time is continually reduced in order to achieve set point. The corrective action continues until the error between set point and process variable is equalized. Figure 1 shows the error from the set point over a period of time under integral correction. Give the error from the set point at each of the following time periods. Next, determine the approximate scale factor used to reduce the error over the following time periods. The error at 10 minutes is equal to 10%. Error at 42 minutes is equal to 2%. The error at 70 minutes is equal to 0.5%, and the error at 90 minutes is 0%. The approximate scale factor between 10 and 42 minutes is 1/5. The approximate scale factor between 42 minutes and 70 minutes is 1/4. Notice the scale factor or gain changes due to integral action. In order to tune the control loop, we need to know an appropriate value for the integral to enter into the PID. One way to do this would be to temporarily increase the gain, causing the level to oscillate. In Figure 2, looking peak to peak, we see that it takes 8.57 seconds to repeat. If we know the number of repeats per minute, we can calculate the integral. A good rule of thumb is to reduce the integral constant to 80% of the actual frequency. Integral can never be set faster than the normal oscillation of the control loop. There are several ways to determine what the integral should be. One method is to use closed loop tuning. Remove the integral equation from the loop, increase the gain until controlled oscillation occurs, and calculate the peak-to-peak time. Integral is expressed in repeats per minute or minutes per repeat. One repeat is the peak-to-peak measurement. This allows the control engineer to see the actual integral response. Refer to Figure 2 and determine the number of minutes per repeat, knowing that one repeat is equal to one peak-to-peak measurement. What value would you suggest setting the integral to? Given the 8.57 time constant between peaks, the minute per repeat value would be 0.14. Using our corrective rule of thumb, we would actually use 0.1785 minutes per repeat as our integral.